The presentation will be recorded, so people can always look at it later on if they so wish. Yeah. Yeah. So good evening, everyone. Thank you for joining. This is our first Physics Journal Club, and I'll just first talk about the big picture goals of the club, since this is our first meeting. All right, so basically the club will be a little bit different from our colloquium. We just want to learn more in depth than what we see in colloquium, because the colloquium, the assumption, you just make things very simple and accessible. But we will be hopefully diving much deeper. So the plan is to just, even from the discussions with different faculty members and the graduate students, that we will get to learn from each other. And the graduate students, the encouragement is that you participate by volunteering to present. You develop your presentation skills and critical analysis and so forth. Yeah. So all of these things were sent in the email. Yeah. So just the structure, it will be every last Monday of the month during the colloquium slot. So hopefully everybody can make it. And basically the plan is that the first 25 minutes will just be a short presentation on the key ideas of whatever paper we're reviewing that month. And then 20 minutes discussion. Hopefully it will be much engaging, it will be on fire discussion. I mean, I'm assuming people have read the paper or skim read it, whichever is the case. So looking forward to the discussion. We'll get to learn more from each other. And then, of course, we try to help each other as graduate students. So we'll have a 5 minutes discussion on different opportunities that graduate students can take a part of. Generally, the last point will be like, we will talk about what paper we'll review next month, but this month our speaker hasn't confirmed yet, so we will update you very soon about the next paper. All right, so if you're ready, we will get right into it because we don't have much time. This is the overview of the presentation. At any point, if I'm breaking or something, you can't hear me, please let me know. I've discovered that the internet always works until you need it the most. So if anything is not working well, just send me on the chat. All right, so basically the overview of the presentation, I'll just briefly go through some basics of quantum computation and discuss the main ideas of the paper, and we get to the conclusion. All right, so that's the plan. All right, so basically quantum computation is attributed to this guy. Many people say he started the whole movement. He said, like, nature is classical, damn it. If you want to make simulation of nature, you better make it quantum mechanical. So we realize that quantum mechanics demands that we do quantum computing. It's not optional. So basically, what are the things that we see in quantum mechanics that is not in classical mechanics? It's superposition. Things can be in multiple states at the same time. There's no classical analog of that. Entanglement is another thing, resource that we don't see in classical computation. Basically, is that the information is encoded in the correlations of the system, not as a part. Those who are experts in this have probably heard John Prenskill explaining entanglement as like reading a book. If you read a book with 100 pages and you read 10 pages, you do not have 10% of the information. If it's an entangled quantum book, you have nothing. The only way you get information is that you consider the book as a whole. So that's what basically entanglement means. And for the guys doing quantum annealing, tunneling may be a good resource for them. So yeah, so basically those are the things that we don't have a classical analog and we utilize in quantum computation. The basics of your classical computer is kind of like this. You have your input, you have your output, and somewhere in there, that's your CPU doing the processing. And if you zoom in this guy, you find that he's made out of different components, which are your gates, AND gate, OR gate, and so forth. And basically, you can do a truth table with this if you have got two states, a state of 0 or 1, which using transistors, this is an easily doable thing. All right, so that's the classical computer we know. So how do we do this in the quantum analog? Okay, so now we don't have a bit, we have a qubit, and a qubit can now be represented as this superposition of two states. All right, and then we can also represent an entanglement as just those two, the correlation between those two states. And this is called the Bell state, all right? Then we can also graphically represent this. This is called the Bloch sphere. So then a qubit can just be thought of a vector that lives in this sphere, all right? So if Z is up, you can think of Z up being spin up and spin down, and anything along the line is just a linear combination of that. All right, so basically that's all the basics you need for quantum mechanics. For those who haven't seen a quantum computer, this is how it looks like. Very beautiful. And what goes on in there, just like the classical analog, you have different kinds of gates. All right, so quantum gates now will be basically your matrices. And so your matrices, you know that matrices are what, when you apply to a vector space, matrices are just like linear transformations. So this now will be just matrices. Then your X gate will basically do a bit flip. If you have your qubit, if it's bit up, maybe 1, it will change it to 0. If it's 0, it will change it to 1. And then you will have another gate called the Z gate, which just does a phase flip. So if you had that relative phase being positive, it can change it to being negative. And if it's negative, it can change it to positive. All right. And then we have a special gate, which is called the Hadamard gate. Basically, if you take in a qubit 0, it will couple it into a superposition, and you have another T gate and so forth. So these are called the universal set of gates. And you can go to Nielsen and Chang book on quantum computation and quantum information and read about different kinds of these gates. It's the same thing as in classical. You have your input and you have your output, and in between that you have your gates that does the processing. All right, so that's the introduction. Sorry, I'm a bit fast. I want to get to the core of the paper, right? So it's the same thing here. These are your inputs, and in between you just have unitary operators, and these are your outputs. And you can always now perform some measurements. By the way, this sign means a control. So that means you either apply that operation based on the state of that other qubit. So you'll see more of that as we go on. All right. So now in just conclusion summary of basic introduction is that this is the gate model. There are other kind of models. There is the analog quantum model, Basically, you just prepare the quantum system and let it evolve. You can't manipulate it in between. So that's just for simulating quantum dynamics. And there's other guys doing quantum annealing, those who have heard of D-Wave. So basically, they work towards optimization problems. I can't remember if it's Om or someone who was working on adiabatic process. It's probably Shahid or something. But yeah, so quantum annealing uses that kind of process. And there are people working on hybrid classical and quantum algorithms. So you basically have your classical computer set the parameters, and then the quantum computer does the heavy lifting of doing the complex calculation. All right, so that's it of the basics. Okay, so I have just a few more points. The goal of quantum computation, the engineering part, they want to build good qubits, stable fault tolerance, but my interest is on the algorithms that takes advantage of this quantum parallelism. And so basically what we want is algorithms that minimize the error and have a high fidelity and success probability. So we'll see that as we look at the paper. All right, so where are we now in terms of, I copied the slide. As you can see, the person who on the slide is over there. His name is Dr. Daniel Park. I have one person who has to mute themselves. Okay, okay. All right, so basically this is where we are. We are in an era of called noisy intermediate scale quantum called NISQ. So we don't have fault tolerant quantum systems yet, but that's something that's coming in the near future. All right, so that is it. Hopefully many of you have had a chance to skim through this paper. So it's titled Preparation of Excited States on a Quantum Computer. That's the general abstract. So I'll just give you a little bit about the authors. So Cheng-Yin Gu, she's a PhD student there at the University of Tennessee. I'm assuming she's the one who did most of the work, but I could be wrong. So she's a PhD student, and then there's a postdoc at Los Alamos Lab, and then Professor Thomas Papenbrock from University of Tennessee, and Professor Asahan. I hope I say that right. Otherwise, the authors will kill me after this. But yeah, so that's it about the authors, just to put a face so you guys know they are real human beings. Yeah, so here's the overview about the paper, and I want to apologize in advance. We picked a paper that was really too dense for such an introduction of a journal club. Hopefully we'll make better improvements. So there are two methods that were discussed there. The first method is the time-dependent unitary evolution. And I'll describe a little bit in a few seconds what these methods do. And then the linear combination of unitaries. So both of these methods are supposed to create an excited state using some excitation operator. All right, so the paper has four things. One, description of these methods. The other one is analysis. So they analyze the errors, the fidelity, the success probability, which is mostly of what you see in the appendix. It's that analysis. And they actually do pick a simple implementation, a single qubit operator, and they test it out and they see how it works. So that was really great. And then they have an application on a nuclear system. All right, so because of time, we won't focus on many things. Yeah, two reasons: because of time, and also some of the things I didn't understand myself. So we'll just talk about the simple method, and I think everybody can be able to understand and relate to this. Yeah, we'll just figure out from the discussion how things went. All right, so here's the main problem. You are given a Hermitian excitation operator O, and your goal it is to find, okay, you are given O and an initial state. All right, so the goal is to find a quantum protocol that you can apply this operator to this initial state and get an excited state. And of course, with some normalization given by that. Now, it must satisfy two conditions. The first condition is that your excited state must be on the same quantum register as the original one. And the second condition is concerning your fidelity and your probability of success. So given those two conditions, can you do this? All right, so what did the authors do? The first thing, the method they use is called the time-dependent unitary evolution. So what they did is they just took this operator and exponentiated and put a parameter gamma. And basically, if you think about it, if this operator is a Hermitian operator, this could be your H, and this gamma could be your T. So now if you've got H and T, sorry, I'm missing an I there. There's supposed to be an I there. So that's now your standard evolution operator in quantum mechanics. And as you can see, which is not difficult, well, if you can convince yourself this is possible, if this parameter is very small, then basically applying a circuit which uses a combination of this unitary operator, you will get the excitation state to be proportional to sine of that. And you can see that sine for this thing, that if it's small, sine will just be approximately whatever it's in here. All right, so that tells you, and then you have got an order, a squared error that comes along with it. All right. And yeah, as I just alluded to that this could be thought of as the time operator, time parameter, sorry. All right, so how do you now do that? So basically, you can first decompose your operator into a linear combination of unitary operators. This can always be done, and you can just make sure that these are normalized into what they call a one norm coefficient vector. Now, they don't explain why they use a one norm instead of the standard. We used to the standard normalization with squared. The summation of these things squared equals to 1. That's the standard we are used to. But I guess someone else can explain to me later on why. Okay, so then this means just the spectral norm. All right, so you see so many parameters in the paper. I just wanted to do some bookkeeping as an overview so you can understand where each parameter goes where. I heard someone talk about this at the beginning. All right, so remember, this is our initial thing, right? So we are given an excitation operator, we are given an initial state, and what we do is we put it in, this is our magic box, and what comes out of there is an excited state. All right. Now, mind you, this initial state doesn't have to be like, it could be a ground state of a quantum many-body system. So it doesn't have to just be a single qubit. Of course, when they did the simple example, they used a single qubit. But you can imagine this as like your reference state. If you are doing Hartree fork or something like that, one of those methods. All right. So what goes into this magic box is a quantum circuit that's related to this unitary operator. And basically, these parameters are now related to that. Those are the ones that come with the decomposition. And this parameter nu comes with the normalization that, and of course we have our fidelity and success probabilities. All right, so that's just the overview. I hope that makes sense. And it turns out, as they do the analysis in the paper, that if you focus on these parameters, you can then define this time parameter. So you can fix what this time parameter should be based on these parameters, of which that simplifies the problem. All right. Now let's rush a little bit. We now have the overview. We see the big picture now. Let's zoom in. So this is the circuit I've been telling you about. So what happens in this magic box is that you have this kind of circuit, this combination of circuit. Now, why this is the case is something they did not describe in detail, but it turns out that the goal is that you want what comes out here to be proportional to that excitation state that we want. So this turns out to be that way. All right, so as I mentioned, this edge is the Hadamard gate, and this symbol means a control U gate, where you can represent it in metric form in that fashion. All right, I'll be a little bit quick because of our time. So you can simplify what's happening here into just a simple metric form like this. All right. And then now we just now simply have to perform measurements. And when we perform a measurement, this is our state that we find. And what's our success probability? Our success probability is given by that. That's sine squared. And you can see when you expand that sine squared, you will get gamma squared. And now this is the main point that's also a problem, is that we wanted gamma to be small to have small errors. Remember, when we started, you want to do that expansion. But then if gamma is small, what we find is that we have a small success probability, which is what makes this method inefficient. So that's why the authors use the LCU method, which is the linear combination of unitaries, and it turns out to have a much better success probability. All right. Then just now, simple example, you can take an operator, a simple operator that just like, acts on one qubit. And what you do with it is that in that basis, you can take psi naught to be 0 and then the final state to be 1. So your operator will just basically turn a 0 into a 1. All right, and then you can exponentiate it. Sorry, I still need a minus I there. That's a typo. Yeah, so then you can convince yourself that's what you get, and that Rx is given as the rotation metric. All right, and so then you can fix the parameter there, and so that's it. That's our circuit, remind ourselves. So then we can fix our time parameter, which depends on this EF is just it's just a parameter that depends on the fidelity, as we mentioned. All right, so that's what they get. Sorry, my time is up. Can I ask for 2 more minutes just to tidy this up, if that's okay? All right, so then, yeah, basically they get a very low success probability because of that. They chose gamma, which is that parameter, to be 0.3. All right. Something that made a little bit more sense to me is looking at the transition probability. Remember, we started from state 0 and we going to 1. And so now when we prepare our approximate state, we want to ask a question: how close is it to the state 1? And this is the transition probability. And it turns out that you can do this either by using the simulator or the real quantum computer. By the way, yeah, you can log on to IBM and use the real quantum computer. And you can see from this is that this is the exact value, and the exact value and the approximate values are close to each other. Mitigated results mean that they just applied some basically some error correction protocols just to minimize the noise. And yeah, that's it. The conclusion is that quantum mechanics demands us to go to quantum computation, and basically any quantum operator, if you represent it in second quantization, you can use the Jordan-Wigner transformations to map it into lowering or raising spin operators. And yeah, and then there are certain steps you can follow. Now we saw that this time-dependent method is not efficient. What we ended up concluding is that you need to follow the other LCU method, which I didn't have time to describe. It has a better fidelity and things like that. Now, this was done in consideration that if you had a fault-tolerant quantum computer, things will be a little bit different. And yeah, the authors also, I like that they use what they came up with and applied it into a simple system, but it's a stepping stone to much more complex systems. And I think people can do this with, I know many people are interested in nuclear physics here. So yeah, we can all jump into the wagon. Now, before I hand over to Elena, I want to welcome a special guest. I invited Ryan LaRose. He's a PhD student at MSU. He's doing quantum computation. And I told him that I'm not an expert in quantum computation. So if you guys have had questions, Ryan will be able to answer them. All right, thank you for listening. I'll hand over to Elena.
Hi, thank you very much for a very interesting talk. And also, I thank you for this initiative that I was trying to encourage some of our students to do the journal club a while ago, and I'm happy it becomes real now. So I think we are open for questions. Do you hear me at all?
Okay. Yes, we can hear you.
So questions, comments?
Hello, MQ, I have some questions, if you can answer. I mean, when I was trying to read the papers, there were two issues which I could not understand. First of all, in your slide 27, you were talking about the noisy quantum computer. So what do we mean by noise? This I could not understand. And the second thing was on your slide 37, we were talking about fidelity and approximate states, which I could not understand from the paper as well, that what do we mean by fidelity and then approximate states. So if you can explain this thing.
Okay, yeah, that's a good question. Thank you, Shiva. Yeah, so what they mean by noise, basically at the moment, the quantum systems that are being used, there's what they are subject to noise from the environment, you know, like a quantum state. For you to keep it to stay as a quantum state, you want it to be shielded from the environment. Otherwise, when you look, remember that in quantum mechanics, when you look, you collapse the wave function. So basically, when they say the system is noisy, they mean that there's that sense of noise coming from the background. In fact, even like if you have a quantum, whatever, a qubit, if you can vibrate or shake the computer, that would be noise enough to sort of disturb the state. Yeah, so that's what they mean in that this is an era. So there's a difference. I was also attending at MSU. They had a seminar called the Quick seminar, So that's how I know Ryan from. And so they're talking about quantum error correction. So quantum error correction and fault tolerance are different. So quantum error correction it works similar to classical error correction, where you have your bit or your information, and because you want to protect it, what you do is you then do redundancy. Like if you have one bit, you just make multiple of them, like 3 of them. And so if there's any error that happened, you then look at them at the end. If all of them are 000, then you know nothing happened. Or if it's 001, then you know there was one bit flipped, and then you can correct for that. All right. So then, but then fault tolerant is supposed to be, so then quantum error corrections assumes that all your gates, particularly, remember we just talked about the Hadamard gate and the X gate. It assumes those gates, you can perform them without any error. And that's not true. So that's why people are looking for fault tolerant quantum computation, whereby they take account of that the gates have errors and all of that. So that's what that whole idea of noise means. It means there's just subject to errors. Another person can answer differently. And then your second question was on fidelity.
Fidelity, yes.
Yeah. Okay, so let me just share my screen. Yeah, so then it's described, well, you can just think of it as it's defined as the overlap between the theoretical state that you want and the approximate state. Does that make sense? So if the state that I want is state 1, and the approximate state that I'm getting is very close to 1, then the overlap between these two wave functions will be high, will be like maybe 98% or something like that. So that's maybe how you can think about the fidelity. But I think there are other ways people can describe it. I don't know. Anyone else has another way of describing it? Yeah, it's supposed to be a discussion.
Yeah, just feel free to talk.
So, sorry about that. I wanted to ask that you mentioned about we have different quantum gates, and you say that those are not perfect. Those have some errors which we plan on like solving it as we progress in this field. So, what are different ways that we can make the gates better?
Oh yeah, that's actually a good question. It's an engineering problem.
Okay.
It depends on the system that I think you are using, because there are people who are using trapped ions, and there are people using superconductors, and I'm assuming they are approaching it differently. I don't know what they are doing exactly, but on the theory side, people are looking at a quantum error correction. So, and the whole idea is that you just, to protect your qubit, you introduce redundancy. And of course, how you do that is quite a little bit tricky in quantum computation, because you can't copy quantum states, right? There's the no cloning theorem. So there's a tricky way that people go around that. Ryan, do you want to comment on that a little bit?
Sure. Well, I think you said it well before, in that it has to do with encoding redundant information. More or less, that's the big idea. For the question in general, I think there's a lot that goes into superconducting qubits and gates, and people do entire PhDs in this, and get paid as full-time researchers. And I don't know that much about the engineering components, but I just know that there's a lot of things going into single qubit gates, 2 qubit gates especially. So it's an engineering question. And then for the on sort of the not engineering side, or the theory side, the idea is you still have these noisy type operations that you can perform, but you do them on logical qubits, which are encoded with this redundancy, so that even if, say, an error happens on one of the gates, so they're still not perfect, but you set up the code in such a way that if an error happens on one of the states, then you're able to detect and correct for that. So I'm not sure how much that adds, but that's pretty much all I can say here.
I guess that a lot of people are very novice on this topic, and we're just thinking of the very, very basics. You guys, Manqoba, you are way above what I can understand. But the very simple physics says that a qubit is two particles in a box, maybe an infinite square well. And you have then two spins. These are fermions. So you have parallel, anti-parallel. And basically what you want to do in this qubit, if you look at those matrices that you were showing in the slides, is basically applying rotations around the z-axis and around the x-axis. And when you do that, you are flipping these spins. So you are constructing different bits of information by the way you have the spins. The problem is that you have many of these qubits, or you want to have millions or billions of qubits, and you want to pack them in a very small space. And when you flip the spins of one qubit, it interacts with the next qubit. So then you have noise, because you want to control the information of every qubit separately. But they, of course, induce flips in the other qubits nearby. So then is when you lose the information. You have the noise, and you cannot reproduce the experiments anymore. That's my very naive understanding of the issue.
So you say the origin of the noise is the coherence, kind of. The problem is in what's happening between different qubits, not within one qubit.
It's mostly the perturbations happening between qubits. Yes, and also the loss of coherence. You want to keep this very cold, superconducting, so you don't have any losses of information, but then the interaction between the qubits makes the local temperature to jump. And then that's where you introduce disorder and you lose information.
Aren't there a lot of practical reasons for the decoherence as well? I mean, anything that generates heat in the system. He showed this picture very early on that looked very similar to a device that one of my other students used for a different application, but it was looked like a liquid helium cryostat along with a pulsed field, which is really just an entropy pump, is what it was that he was showing. And anything that generates any amount of heat, including things like electronic noise, cosmic rays, whatever, it just builds up that heat and always contributes to the decoherence, as you call it. I think in that respect, there's a lot of practical limitations to what we're doing. I was just talking to someone a couple days ago about what they're doing at Oak Ridge. This NERSC center they have, noise-induced decoherence, where they're spending a lot of time trying to build up the number of qubits in a system. I don't know, maybe they're up to 100 or something like that, maybe, while reducing this decoherence. And you're always fighting entropy. I mean, the universe would be awesome if we didn't have entropy. But is that kind of a correct assessment there, Manuel, or is that?
Yeah, basically that's it. You want to get quantum entanglement and to form the qubits. So basically, Bose-Einstein condensates. But as you said, there are so many perturbations that will raise the temperature that limits the size of your condensate. And that limits the size of how many qubits you can put in. And if you put more, then you have too much noise. If you put less, you need to increase the size of the condensate. And we don't know how to do that either. Yeah.
Yeah, I do want to just chip in that though the decoherence problem has not been solved and so many engineering problems, there are practical things we can do with quantum computers at the very moment. And I think Ryan, they published a paper on this. So they are what they call hybrid algorithms, which are variational quantum algorithms. Basically, what they do is that, okay, the cost of your function that you are looking for is evaluated by the quantum computer, but all the other parameters that you will need for the variational algorithm, they are, we use the techniques of machine learning and all of those things that people already know how to use in a classical computer. So you just set the parameters on a classical computer and then use the quantum computer now to sort of like evaluate the cost of the function. Because this is an iterative process, even though you have noise, the hope is that eventually you get to whatever, if you are looking for a minimum energy state. So yeah, so they even the quantum computers now that are still noisy, they have like uses and yeah, so it's not an entirely hopeless case. Yeah, I just wanted to add that because yeah, when we analyze the decoherence problem, it just takes us to be gloomy and sad. But yeah, there are a lot of things that can be done at the moment.
Any other questions? I had a question, actually a couple of questions. Maybe I start with a simple one. On the previous slide, I think the slide you were showing before, it was written that phi e must be on the same quantum register as the original state. Why is that?
Thank you for asking that question. I also wrote it down myself. Like it's a question that they didn't explain in the paper. I'm thinking the reason is because you want to calculate the fidelity, so you want to calculate maybe the overlap. I don't know, maybe, but usually, yeah, because yeah, maybe it's because of this, but I don't know exactly why it should be on the same quantum register. Because when you're doing the measurement, you project it on a particular basis, and you sort of like, I don't know if I have, I don't think I.
But maybe we understand it better if we know what does it mean to be on the same quantum register. This should be a very basic question. What is the quantum register and what does it mean to be on the same quantum register?
Yeah, so the register, I'm just trying to pull up the paper with maybe a better diagram or this diagram. Oh, sure. Can you see my screen?
Yes.
Yeah, so yeah, if you have this as your ancillary state, basically when you initialize this will be your quantum register. For instance, this state could be composed of 10 or even 15 qubits. So they are all in the same quantum register. And when you are doing this operation, you have it on the same quantum register in the sense that when you then read out, do the measurement, you are able to project it to maybe like a classical register. Because normally when you initializing states, you define your classical registers and you define your quantum registers. And then when you do your measurements, you take the data, you send it to your classical registers, and then that builds the statistics, and then you repeat the experiment so many times, and the probability distribution is what tells you what you need at the end. I don't know if that answers your question, but
can I say that?
Yeah,
Sorry.
go ahead. Yeah.
Can I say that this is a set of qubits? The register.
Yes. Yeah. Oh, yeah. So you mean what? A quantum register? It will be just where you're storing all your qubits. Was that the question?
Yeah, basically.
Okay.
Yeah, what is physically? It's the physical meaning. Yeah, another question I had was regarding the transformation of the Hamiltonian, because what I was taught, the very basics, was talking about transformation of the Hamiltonian. So that was typically supposed to be the first step. Take your Hamiltonian and transform it into the basis of Pauli matrices. So if you have your Hamiltonian, for instance, in second quantization representation, then it's straightforward, right? Then you transform it, and then in principle, it's clear how to do this circuits, because this will be just one-to-one mapping of your transformed Hamiltonian. So in this paper, I didn't find anything like this. Is there something behind the lines there? Because I didn't even find any Hamiltonian.
Oh, yeah. So the assumption, I think what you're talking about is because the assumption is they are doing an excitation on a ground state. So if you had your Hamiltonian, it will have one piece with the non-perturbative part, or with the piece that doesn't have the dynamics and the piece that has the dynamics. So I think maybe what they are doing is that they are just assuming this. You have a ground state, and then you are now exciting from the ground state, and that operator O actually it has the same units as the Hamiltonian.
Well, it has the same units for sure. It should be something like external field. But my point is that the structure of the ground state can be very different. I mean, it can be very simple ground state like Hartree fog, or it can be very strongly correlated ground state. And similarly, the excitation operator can be different. It can be just one body operator, either a form, or it can be two body, or it can be very complex too. So that's why I'm just wondering if this algorithm they're discussing is general and works for any Hamiltonian and any excitation, or is there something like, or there are some assumptions like this objects? Because I didn't find anything specific.
Yeah, I didn't see a discussion where this could be limited, but I don't have much experience on this maybe to answer clearly. But from what I saw is that from the analysis, the operator was a general operator O, and then they just picked an example to show that with a very simple one cubic operator, this can still produce the results that you anticipate. But yeah, I'm assuming they didn't say there are limitation on what Hamiltonians can be used.
No, they say it's general, but I'm just wondering
is that a valid claim? I don't. Yeah, their claim could not be valid. That's very true.
Yeah, I'm just wondering if the procedure for simple Hamiltonians or for complex Hamiltonians is the same.
Yeah.
Things like that. Okay, maybe I should go over this again.
Yeah. Oh, yeah. Thank you.
Manqoba, can you share your slide where you show that your time parameter depending on energy? So the second method you were showing. Probably at the end or near to the end. The second method, the linear dependent method.
Yeah.
So like that time parameter was dependent on energy, right? In one slide you showed that. Can you go to that slide? I don't know the slide.
Yeah, no, I see that. Yeah. No, so yeah, so this is not the energy. Sorry, I'm sorry. This is not the energy. This is called the target infidelity. So basically, yeah, this doesn't have units.
Okay.
Yeah.
So I was like wondering what kind of thing. I mean, your in your previous method, your time parameter was not less enough, so that your efficiency was not what you demand for, right? But now you said like your second method was good enough than your first method, and your second method, this time parameter depends on that EF. So I was wondering like what is exactly this? How you can control this EF so that you'll always get your time parameter that you want for.
Yeah, so this is maybe like a better way to think about this EF is your error tolerance. If you have an algorithm, you set how much error tolerance you want it for it to truncate, isn't it? So it's in a sense like that, an analogy.
So that means basically that is under your control. Is that true?
Yeah, this is under your control.
Okay.
Yeah, you set this, you decide how best you want this. Of course, you want so this is actually, I don't know why they keep on changing. This is infidelity. You can think about it as the opposite of fidelity.
Okay.
Fidelity, it measures how close are the approximate state and the target state. And this measures the opposite, how unclose. Yeah, I don't know why they mix the two, but yeah.
Okay, thank you.
Yeah. I think our time is up. I'm not sure. So that we respect. So we will have. I don't know. I don't know if there are other questions. Before we just discuss a few, we give it to Khushi to talk about some things as graduate students. Is there any pending question? Okay. It looks like people are already distracted. I apologize once again that this was a paper that was not so very, very accessible. It was, yeah, we'll do better next time. We'll try to make it more accessible. Right, Khushi?
Manqoba, can you allow me to share the screen? It says it's disabled.
Okay, yeah, go ahead.
All right, I'm here to talk about the opportunities that we have. So the first one I wanted to mention was the graduate student research grant, and its deadline is day after tomorrow by 5 p.m. So they give you funds up to $1,000, and each grad student can get this grant for maximum like 3 number of times. So if you haven't applied, then you have 2 days if you want to prepare the application for that. The other one is the graduate student virtual conference grant. That's that its deadline is also October 28th by 5 p.m. and the award amount will be $250. Again, so basically as a grad student, you can get 3 grants in total. So it could be all the 3 research grants or all the 3 virtual conference grants or mixture of this two, summing to 3. The other opportunities are, we will send the list of different scholarships and funding opportunities that we have, and these are different names with their different deadlines. The ones which are marked with star symbol like this here, those are open to non-US citizens, so for international students, and others are only for US citizens. But yeah, and when I came here for my first year, I had a fellowship from American Association of University Women. So I encourage you to apply if you want to. I don't know if we have any female students attending right now, but otherwise also try applying to this funding opportunities, because if you get it, it would really shine like a star in your resume. The other opportunity is, it was mentioned that American Association of Physics Teachers is having their winter meeting in January from 9th to 12th. It is virtual, so if you want to attend that. Manqoba mentioned about this virtual conference, Practical Quantum Computing Conference. And the last one I wanted to mention was the online workshop on advances in many body theories, from first principle method to quantum computing and machine learning primary tabs. So that is all I have got. Thank you.
Thank you.
Thank you, Khushi. Thank you, Dr. Litvinova, and thank you everyone who participated. Hopefully next time we'll be much more interactive, and yeah, I please encourage you to read the paper before coming so we can have a much more deeper discussion. And thank you, Ryan, for joining us. Well, this is the Western Michigan team. Thank you, and Shiva for our organizing, and thank you to Dr. Femiano. Otherwise, all good things are always less than 1 hour. After 1 hour, things start to spoil down. So thank you. Hope to see you next month.
Thank you. See you.
Thanks for the great talk.